This recording is to help you with lesson 3.02, logarithmic functions and their graphs. Alright, we are going to start by just practicing switching from exponential form to logarithmic form and vice versa. We learned this in Algebra 2 quite a bit. We focused on fixing and switching between the two forms. So hopefully this is a little bit of review for you. We're going to take, if we notice the example, it says log base 5 of 25 equals 2, and that's in logarithmic form. To change that to exponential form, we would say 5 squared equals 25. So we always take the base, and your exponent is what it equals, and we set it equal to whatever number is next to it. Now, we don't have a base in our example in number 7. So that's the first thing we need to figure out. What is the base of natural log? And natural log has a base of e. So really, I can rewrite this problem as natural log of base e of 1 equals 0. And remember, if there's no base in logarithmic functions, that the base is 10. So if it just says log of 25, remember, your base is actually 10. Right? We can change this, so the base is e, my exponent is 0, and I would set it equal to 1. So that is how we can get our answer if e to the 0 power equals 1. Alright, let's change it the other way around now. So we are going to take log base 81, and this is the base here. Remember, the exponent is what we set it equal to, so 1/4. And the 3 goes next to the log base 81. For the next problem, you're simply going to use your calculator. Everybody should have a natural log button on their calculator. It appears right under the log button, and it's right next to the 4. So on the left-hand side of the 4, you're going to see an LN button. Make sure you can find that on your calculator, and all you're going to do is push that and hit 18.42 and enter. And you should get your answer of approximately 2.913. For the next one, we need to describe the relationship between the graphs. So if we were to graph these on our graphing calculator, we should get something that looks like this. And these graphs are inverses of each other because they are reflected over the line of y equals x. And we also should know that right away because I can change this to exponential form and this to logarithmic form, vice versa there, and you should get the other equation. And we know that switching between exponential form and logarithmic form, those are actually inverses of each other. So it should work out that way, that yes, these are going to be inverses of each other, just looking at the graph. Next is use a graphing calculator to graph the logarithmic function, and then we're going to figure out the domain and any vertical asymptotes and x-intercepts. So if you're dealing with logarithmic functions, note that your domain has to be greater than 0. Because if you get 0, you have an error that occurs on your calculator. Right, so we're going to look at natural log of x minus 2. This part inside parentheses has to be greater than 0. So if I work on solving for x, I can add 2 to both sides, and I get x is greater than 2. So this can be your domain if you prefer to leave it like that. Or you can write it as an ordered pair. Now, vertical asymptotes, remember that is where you get your error. So at what number will you get your error for the domain? Well, set the x minus 2 equal to 0 and solve. You get an error when x equals 2. So that is going to be your vertical asymptote. And lastly, for the the x-intercept, we plug 0 in for y, and we solve for x. So let's change this to exponential form. So remember, my base is e. My 0 becomes the exponent, and I set it equal to the x minus 2. All right, remember, e to the 0 is the same thing as 1, because anything to the 0 power is always 1. Don't forget that rule. And if I add 2 to both sides, I get x equals 3. So the x-intercept is 3, 0. All right, next we can graph this on our calculator, and we are going to figure out the domain, where your function is increasing and decreasing, and what the relative minimum or maximum will be. So graphing this, I should get something that looks like this over here. I notice that the domain is x is greater than 0, and I have that because of this right here. So if you like to rewrite that as x is greater than 0, you can. And then you're going to use the trace feature on your calculator there, or you just scroll with the arrows right off the bat. And we know that from 0 to this point right down here, which is about 0.368, that your graph is decreasing, it's going down. And then from 0.368 to infinity, because we don't know what number it actually stops at, your graph will be increasing. And obviously the lowest point on your graph is a minimum, and that occurs at approximately 0.368 and negative 1.5. Lastly, we have this model function for 83, and we're already given the equation for us, which we're lucky in that fact. So for 83, it says use a model to approximate the length of the mortgage if the monthly payment is 1316.35. So what we're really doing is we're just plugging this numerical value in for x and solving. So you can do that on your calculator quite easily and get approximately 30 years, or you can find the 1,316 on your graph, and we'll follow the dashed blue line up until we hit our graph, and it'll hit our graph at approximately 30, y equaling 30 years.